You talk to AI every day now. ChatGPT, Claude, Gemini, you ask a question in plain English and it just answers. Not long ago, this was impossible. Computers needed code, precise syntax, specific commands. So what changed? How did computers start understanding language? It starts with a key building block called word embeddings. They are how computers learn what each word means and how it relates to every other word. In this video, we will learn what word embeddings are and how they power literally all of modern AI. Let's get started. Take a word like cat. How does a computer know what it means? The idea is surprisingly elegant. You turn it into numbers. Not just any numbers, a whole list of them, hundreds, sometimes thousands of values that together represent what a word means. This list of numbers put together forming a so-called vector. And the brilliant part, nobody handcrafts these word vectors. A model reads billions of sentences and learns purely from context which words appear near each other. The result's a map, a space where every word has a position and similar words end up close together. Cat lands near dog and hamster. Pizza lands near sushi and pasta. The distance between words captures how related they are, and this is called a word embedding. Now you can see why. Words are literally embedded in space. In 2013, a team at Google built a model they called word2vec, as in word to vector. The idea was simple. Take a neural network, feed it billions of words, and train it on one task. Predict which words appear near other words. The vectors the network learned along the way? Just a side effect of that training. But when the researchers examined those vectors, what they found stunned the AI community. They took the vector for king, subtracted man, and added woman. And the closest vector to the result was queen. King minus man plus woman equals queen. Nobody programmed this. It emerged from patterns in text. It wasn't a fluke. Paris minus France plus Italy equals Rome. The model was never told that Paris is to France what Rome is to Italy. It figured that out on its own, just from reading text. This was the moment the world started taking word embeddings seriously. Let's see this in action. We've set up a real experiment. We picked 100 words across 10 categories: food, animals, sports, music, science, and more. Each category gets its own color so we can track where words land. Then we embedded every word using two popular word embedding models. The raw embeddings have hundreds of dimensions, way too many to visualize. So we used a dimensionality reduction technique called tsne to compress them down to just 2 dimensions, a flat map we can actually see. Here's our canvas, and there's cat, our starting point. First, the animals. Dog lands right next to cat, just as you'd expect. Elephant, dolphin, tiger, they all cluster together. Now food, pizza, sushi, pasta, they form their own tight group away from the animals. Royalty lands in its own neighborhood. King, queen, prince, crown, all bundled together. Sports pulls to yet another region. The model knows these are all different domains. Music finds its own corner too. Science clusters neatly. Now here's where it gets interesting. Math and programming. Notice how math, science, and programming are all neighbors? The model sees these fields as deeply related. Now look how far away food is from all of them. Pizza and sushi have nothing to do with equations and algorithms. And the model figured that out on its own. Same story with history and politics, separate clusters but close together. The model captures that these domains overlap. And look where Gladiator ended up. We had it under history, but the model placed it right next to the royalty cluster. In text, gladiators live alongside emperors and thrones, so the model places them together. Already a hint that embeddings capture usage, not categories. Now, one word we haven't talked about. Python. It's both an animal and a programming language. So where does it land? Right in the programming cluster. Remember, these models are trained on text from the internet. And online, Python appears overwhelmingly in a programming context. It is the most popular programming language after all. That's the key insight. Embeddings don't capture what a word is, they capture how it's used. Now let's compare. Same 100 words, same colors, but a completely different model. On the left, Model A, the one we just explored. On the right, Model B. The layouts look completely different. The clusters are in different positions, different orientations, but the clusters are there. Let's simplify. Now look at this. See how food sits off on its own in both models, completely separate from everything else. Pizza has nothing to do with algorithms. And math and programming? Neighbors. In both, the models agree on which fields are related. History and politics, close together on both sides. The absolute positions don't matter. What matters is the relationships. Both models independently learn the same structure of meaning. That's what makes embedding so powerful. So where does this fit in the bigger picture? Every large language model, GPT, Claude, Qwen, starts right here. You type a sentence. The model breaks it into tokens, pieces of words. Each token gets converted into an embedding, a vector just like the ones we've been exploring. Those embeddings flow into the transformer, the architecture that powers modern AI. And out comes a response. But don't underestimate this embedding step here. It's not just pre-processing, it's the foundation. Everything the model knows about meaning, context, and relationships, it starts right here, in the embedding layer. Word embeddings aren't just an academic curiosity, they're the first thing that happens every single time you talk to an AI. So far, we've embedded individual words, but what about entire documents? Take an article about Italian cooking. It contains words like pasta, olive oil, basil, a recipe. So how can we get a document level embedding from those? One simple idea, just average all the word vectors in the document. That's your document embedding. Now you might say, really? Just average them? And that works? Yes, surprisingly that works. Now, modern AI systems do use more sophisticated techniques, but the core idea is the same. Take word embeddings and convert them to document embeddings. One list of numbers that captures the meaning of the whole piece. Now imagine doing this for thousands of documents. Each one becomes a point in space. Cooking articles cluster together. Tech articles form their own group. Sports coverage pulls to another region. Store these vectors in a database, and you've built something incredibly useful. A system that understands meaning, not just keywords. We've been saying vectors are close or far apart, but how does a computer actually measure that? It comes down to direction. Picture two arrows starting from the same point. If they point the same way, the words are similar. If they point in completely different directions, the words are unrelated. This is called cosine similarity. There are other ways to measure distance between vectors, but cosine similarity is by far the most common. Forget the formula. Just think about the angle. When two word vectors point in almost the same direction, their similarity is close to 1. When they're perpendicular, 0. No relationship at all. And if they somehow point in opposite directions, -1. Let's see it in action. Cat and dog both point in a similar direction, high similarity. Cat and algebra, completely different directions, near 0. This is how a computer answers the question, are these two things related? It checks whether their vectors point the same way. Now let's look at what's like the most common application of word embeddings in industry, semantic search. But before we got semantic search, we had keyword-based searches. Traditional search matches keywords. You type hungry, you get results that literally contain the word hungry. But what about an article titled Quick Weeknight Pasta Recipes? It's exactly what a hungry person wants. But the word hungry appears nowhere in it. Semantic search works differently. It embeds your query into a vector and finds documents whose vectors are closest in meaning. Now, hungry surfaces, cooking articles, restaurant reviews, meal planning guides, all related by meaning, not by matching letters. This is what powers modern search and tools you use every day. Every time a search engine seems to read your mind, there's an embedding working behind the scenes. Second application, recommendations. Say you just read an article about machine learning in healthcare. The system has already embedded it as a vector. Now it searches the entire vector space for the nearest neighbors. Every dot here is a different document. And zooming into our article's neighborhood, an article about AI-assisted diagnosis, close in meaning, a piece on neural networks and drug discovery, also nearby, and one about data privacy and medical records, related domain, slightly different angle. This is the you might also enjoy sidebar. No manual tagging, no category labels, just vectors, distances, and meaning. A word embedding is just a point in space, a list of numbers, but those numbers encode meaning, context, and relationships between ideas. We started this video by asking this key question: how did computers start understanding language? Well, now you know.